I don't think it's any sense to wait.
Yeah.
We can start. For today, I want to take a subject that is called Hilbert's transform. It's one of the bright David Hilbert's ideas. Let's say we have a signal what can be represented as a sum. Say, starting from 0 to infinity, a cosine omega plus some pk. Or sum starting from 0 to infinity of a cosine omega plus sk sine omega. Our classic Fourier rule. It's a periodic signal represented as a classic Fourier. One second, it should be C. Cosine. Yeah. This is correct. It's simple. Here, A is a square root. Square plus is square, and pk is minus r from sk divided by ck, always classic. Nothing new, nothing special. Let's take a look from the, let's say, another perspective. This one is some angle. Angle changes in time. Classics of geometry. We have something multiplied by cosine. If we have some vector with the angle, say C, the red one if length of this vector is a, this red one will be a k cosine c. Classic geometry. In our case, red one is a cosine omega plus pk. But if exists a horizontal projection, or let's say it will be real and this one will be imaginary, exists also vertical. The green one also exists. It's a classic geometry. And it will be a k sine of xi. So in theory, exists something a sine of a omega plus pk or sine of, it must be correct. So exists sum equals to sum of sine omega minus sk cosine omega t. We can call it a conjugated signal. If exists our signal represented with the Fourier rule, exists also a conjugated signal. If our signal is a projection to the real axis of some vector, the conjugated one is projection of the same imaginary vector to the vertical axis. All right. Clear. So Hilbert introduced a conjugated signal beings from 0 to infinity of cosine factor multiplied by sine of minus sine factor multiplied by cosine of k omega t. Conjugated signal. We have S plus 1. At the vertical we have sigma. And the sum yields us something. What's it something? 1 second. If it's a time square. And here, for example, our signal. If we connect all the maximums, drawing so-called borderline, And this one will be our time. This line m from the maximums is a square root. Sorry, what I'm doing? Square plus by the Pythagoras theorem. This formula describes a borderline line connecting maximums of our signal. It's like a limit. And we also can say an angle or instant phase. It should be minus r tangent sigma divided by s. It's an instant phase. It's like our signal being drawn by vector with variable length and angle, like in polar coordinate. Like we have a draw, which changes both in angle, in angular dimension, and in length. So at any time with this transformation exists a vector drawing this green line. In fact, it draws our signal. Introduction of conjugated signal allows or conjugated signals allows us to represent any signal that can be decomposed or represented with a Fourier law as a vector. Some remark on the borderline. At the moment when a conjugate is 0, the borderline equals to our original signal. Also, at this moment, derivative of our signal equals to derivative of the border line. And borderline always greater or equals to the signal line. So that's why it is a borderline or limiting line. most probably we will deal with the signal, our signal that decomposed with a limited frequency range. Let's say what signal energy is from omega low to the omega high. And difference of is much lower when the average let's say we have central frequency omega 0 being by half. We have signal with limited and relatively narrow frequency range. Zero, maybe zero, it's not the average. I have used zero. Idea of such signal it will be something somewhere similar to harmonic signal with slowly changing angle and amplitude. Full phase can be represented as some, let's say, omega average. Omega average plus some maybe it's not multiplication, it's a function. This function of angle change in general changes quite slowly because we have a narrow frequency range. In such case, conjugated signal can be represented as an integral transform. The good news about this transform, what it's invertible. We can get a signal as 1 against p in minus infinity to infinity. Then we stop the top. We have a clear connection between signal and its conjugation. It's a pair, or exactly this pair is bears name of Hilbert transform. What good with this pair? It is not dependable on period. If our previous idea was applicable only to periodic signal, this one for any. So with the help of this transform, anything, periodic, aperiodic, can be represented as a vector. The only problem is moment when tau equals 2. That's why it should be applied as a limit. So if you integral in infinite Hilbert, infinite limits, tau, the tau should be taken as a limit epsilon to 0 of infinity epsilon s tau, the tau plus epsilon to infinity s tau minus tau, the tau. It is quite easy. So, the idea of Hilbert transform, this gives ability to set a vector representation for any signal. It can be harmonic or non-harmonic, it can be even non-periodic. It will be represented with the variable vector. For each vector having real and imaginary part, where is the vector? Complex function. We can, with the help of Hilbert transform, we introduce a complex signal. Thinking what our real signal, what we observe in our time space, is a real part of some complex signal. This one exists in time and it's real. This one is a conjugated and imaginary. So, the borderline is nothing else than the absolute value of complex signal and being a square root of square plus square. Its argument being tangent. Imagine against the real equals to the, hey, what I'm doing? Remember basics of electrotechnics. When AC current or voltage was represented as a vector on a complex plane. With the help of Hilbert transform, anything can be represented as a vector on a complex plane. Now let's ask a question about frequency. representation of conjugated signal. Let's say we perform a Fourier transform of a signal, and we got what we got? We got as omega. It's spectral function. Now question about cosine of omega. It should be a result of Fourier transform of a conjugated signal. We need to find integral from minus infinity to infinity sine a power omega time. If we apply a Hilbert's formula, question will be to do something with the integral. If what Hilbert's formula application gives us instead of sigma, what should we do? We will replace time with the clicking stop. Anyway, E equals to dV in such case. And replace a power j omega using the Euler formula. So we will have to 1 second, why time? Frequency. We need to integrate in infinite borders s no tau at power your omega tau d tau, and this will be multiplied by in margins cosine omega v minus your sine omega v divided by pv and by v. Looks not very simple, but direct calculus. Well, this shows interesting thing. It produced square root from -1 in case omega is negative, and minus square root from -1 if frequency is positive. Looks terrible, but very easy to solve. Now the green one. It's nothing else than the spectral function of our signal. So we can write down the following. Spectral function for conjugated signal will be just multiplied by spectral function of our original signal at the negative frequency and minus yod gs at a positive frequency. Spectral function for complex signal will be just sum of spectral function of real signal plus multiplied by the spectral function of the imaginary signal. Because it's very easy. Fourier transform is linear, so transform of the sum equals to the sum of transforms. It is very easy to see what spectral function of a complex signal equals to gs omega plus yod multiple, okay, yod gs omega equals to 0 at the negative frequency and gs omega minus plus yod minus yod gs omega equals to double gs omega at a positive frequency. Inverse Fourier transform for such case is known one against double P in terms of imagine omegas power yod omega P, sorry, the omega. K is Fourier transform, allowing to get this complex representation from its spectral function. What? How? Very easy. One moment. Equals to 1. From 0 to infinity we need to integrate. Our original signal spectral function f power d omega. Yes! We can get our complex representation directly from signal spectral function. Classic theory of circuits or basic of electrotechnics operate with harmonic voltages on currents. Let's say we have harmonic signal being cosine of omega 0 plus some p0. We can write it as multiplied by cosine p0 cosine omega 0 minus sine of p0 multiplied by sine of omega 0 time. Easy. Conjugated for this one will be, we need a conjugated one. Conjugated one will be max cosine p0 sine omega 0 time plus or plus sine of p0 cosine omega 0 time. Or I can write as if S was cosine omega 0 time plus p0, conjugated one will be U maximum sine of omega 0 time plus p0. and a complex representation complex representation will be plus j of equals to cosine omega 0 time plus p0 plus sine of omega 0 time plus p0 on which is equal a power j omega 0 plus p0. If we introduce a complex, let's see, we can introduce a complex amplitude of a power j p0 if we introduce a complex amplitude, our complex signal will be complex amplitude multiplied by a power 0 time determine the synchronous speed of complex plane rotation. We got a Steinmetz Heaviside symbolic representation. While all currents and voltage are synchronous, we can omit rotation of the complex plane. While they are synchronous, it is not important for our analysis their vector position against time x. The only important is mutual between vectors. So all basic idea of electrotechnics theory, all this Heaviside Steinmetz representation is one particular case of harmonic signal of Hilbert's transform. Signal theory, all electrotechnics is one case of signal theory. Signal theory gives us tools for any signal. We can represent as a vector anything. only one moment. The required conditions must apply. We can represent as a Fourier row, and this one requires a Fourier row. If the required conditions are not met. Okay, I think it's enough for today.